Out of curiosity, how many people in here have played Atari Adventure? Would it be everyone in the room? Yeah? Okay. And how about Colossal Cave? Okay. So no point me doing long demos. I was actually thinking about starting up and doing a little fly-through real quick. Maybe I'll do a couple seconds of it, just to kind of refresh everybody's memory. It's probably been a couple years, right? Do-do-do. Move over, Twitch. All right. This is kind of an important moment. Do you guys call this a sword or a spear? Spear, right? Yeah, the box says sword. I'm going to talk about that a little bit. Yeah. Oh, let's see. I'll be crazy and go kill the other dragon real quick. Make my life easier. Ta-da. All right, this is level 1, so I don't have to worry about the bat stealing things, right? If everybody remembers the bat flying around.
That darn bat.
I know, right?
Why can't you kill it?
Like that flickering. That's a big part of my childhood memory right there, that flicker. And wondering why this happens, which is probably why I learned any code at all. I'm not going to talk about this bridge too much, but it's an interesting way to deal with bugs. Oh, I lost my key in the wall. Well, we'll just make a bridge so you can go get it instead of fixing the problem. But rightfully so. That magnet's nice, too. I don't remember a lot of magnets in the Middle Ages or fantasy period here. Atari called this a chalice. I always thought it was a trophy. Right?
Like a goblet.
Goblet, yeah, right.
Depending if you drink out of it or not.
Right. Woo! All right. Okay, so that's everything you ever wanted to remember about Adventure, except the bat and the other dragon, right? Yeah.
And the secret.
And the secret dot. I'll have to talk about the secret dot. There's no way around it. So let me start and introduce myself a little bit. My name is Wil Lindsay. Some of you may have caught my workshop on Friday. Boy, I'm echoing a little bit up here. I am a professor. I am the director of the game design program at Rider University. I teach all sorts of game design stuff. I spend a lot of time in Unity and Unreal Engine, working on 3D. I do a little bit of 3D printing. But this little piece that we're doing today seeps into my classrooms all the time. And in fact, I teach classes that are more related to the history of game design, which is, it's kind of strange teaching something we're calling history when all the, everyone involved is mostly still alive. So it's a living history, I guess. But I think it's really important, and for my students who, some of them have never seen an Atari in real life, I think it's really important for them to understand why we're doing this and the fact that everything that they're doing in games today is rooted in what happened years and years ago on these old systems. And a lot of the legacy and culture stayed the same. So I'm also a kind of a strange professor. I don't give tests, and I don't think it's that important to know specific dates and things like that in history. I teach hands-on. So in my history classes, you get to code in assembly language. And you may not be good at it, but I think that's definitely a way to learn, and learn what it was really like. And again, get a better understanding of how close everyone was to the hardware. Before I really get started, I also want to talk about this gentleman. This is Warren Robinette. Warren Robinette is the designer of Adventure. Is he out here? That would be awesome. Maybe he's on YouTube right now watching this and shaking his fist at me. I hope not. If again, I'm still meeting some of these people, and I've reached out to him a couple times without luck. A lot of the information that I'm going to talk about today comes from secondhand sources. I feel like it's pretty reliable. Anybody who's worked close to the hardware understands the inferences I'm making here. So I'm not stretching anything, but it's kind of hard to guess intent sometimes. So if you recognize any of this, or if I mention your name in the talk, I would love to talk to you, and make sure that I'm teaching my students the right direction and the way things really happened. Let's see, where do we begin? Oh, Warren, yeah, we should mention the Easter egg for a second. So Warren's claim to fame has a lot to do with the game industry and the politics of it. And of course, he's well known for hiding his name in adventure. I couldn't have gotten to it from the level I was on, but everybody knows about the tiny microdot that you would have to carry around and find with the bridge in an invisible maze. I don't know how anybody ever found it, but apparently a year or so after Warren left Atari, a kid wrote a letter and said, "Hey, where's my prize? I found the thing." And this is also a history changer, but in a different way. This talk is not about that. I'm not really interested in the politics of what happened. I'm interested in how the technology impacted our lives. So let's jump into it. This is Atari. Released in 1980. Again, Warren Robinett. This is one of the things that I like to push on my students a lot is the fact that in this era, this was a one-man job. So it took him about a year. He did all of the art, all of the design, all the coding, and when we look at the coding, that by itself was a beast. This is a lot different than the games my students play today, where there'll be 50 people here in the US working on a game, and then 300 more in China or in another country, filling in graphics and things like that. They're produced like movies now. And again, I think it's really important to look at this route. And it helps understand why things happen. I am particularly interested in adventure because it's a genre starter, right? So this whole action-adventure idea, there are other graphic adventures out there. In fact, let's see in my notes somewhere here, Ken and Roberta Williams' Mystery House, 1980. These text games with graphics involved. And I also think that's an important part of history. But there's something dramatically different that happens when you start mixing the storytelling with these original arcade mechanics that were frankly meant to entertain us for under 2 minutes. And I think that's where history changed. And I think this game has a lot to do with that. Warren openly talks about the fact that he played Crothers and Wood's Colossal Cave adventure. He openly talks about it, so we know it happened. So there's no big secret to that. The majority of this talk, I just want to talk about that relationship and what that means to kind of transcend media like that while you're a producer. And it left a really heavy impact on game design today. My understanding is, let's see, this was originally written, I hope I got the right machine in this picture, right? Crothers' code was written in Fortran. It ran on a PDP-10, and it was released on ARPANET, so before the internet, somewhere around 76, 77. I'm not absolutely sure about that one. Warren, to my understanding, Warren had a roommate who worked at Stanford's AI lab, where Woods also worked, so Woods was developing this game. And so he had an opportunity to go to Stanford and actually play it on a PDP-10. There is, I don't think I really need to talk about what happened here in technical terms, but anybody who's played this has a good understanding of what it is and how it works. And the fact that the idea crossed his mind that he could somehow port this concept or port this game style to an Atari 2600 that didn't even have fonts. It's kind of an interesting idea. So again, I don't need to talk about the differences in the technology. It's kind of a crazy idea. I will talk a little bit about the Atari itself. I think that's important. These programmers were working under some amazing constraints. There's that guy, yeah. 128 bytes of RAM. That's what he had to work with. I understand that to be a quarter of a tweet, which is kind of amazing. So my little speaker in my living room spends more variable RAM telling me the weather when I could have looked out the window. Yeah, it's kind of amazing to think about. The original cartridges were designed to be up to 4K of ROM. I had some, over the years that I've been teaching this, I try to convey to students how tight that is, how little that is. And it's hard to do because, frankly, you know, I looked at the specs this morning. My little watch, which is an older watch, has literally 1,000,000 times the amount of ROM space. This is a tiny, tiny space that everyone was coding in. Getting behind on my slides here, rambling away. So there's the guts of it. I did a talk on Friday, so if you want to hear more of the technical aspects of the Atari, that was more of a hands-on and looking directly at the assembly code for this machine and the memory maps and things like that, so I won't get into that. This is kind of an interesting thing to think about, the input, right? So we had something close to a QWERTY keyboard on the PDP-10, and this guy has 9-pin serial to joysticks. There were other interfaces that could be produced, but basically this is the entire connection between the player of the game and the machine. All the input came through that. These guys had up, down, left, right, and a fire button, and that's it. So you have basically 5 bits of information that you can convey into the machine. That's a lot to think about when you look at the other games that are out there. There is this remarkable chip that was designed to go along with this. So the Atari was based on a 6507, which is a cut-down version of 6502 processor. Everyone in the room probably knows that one well. It had a few less address lines to it. It was missing some interrupts and some things that aren't that important to game design, and it was cheap to produce. So I'm kind of glad they did it that way. The associated chip that allowed it to talk to the television is referred to as the TIA chip, the television interface adapter. When originally designed, you have to remember what people were expecting of arcade games, and it wasn't much. And when we look at the following years that go all the way up to the video game crash in 1983, there was some amazing coding that happened on that. And I talk a little bit about the color palette in my talk on Friday that's still kicking around on YouTube. It was originally designed to show 4 colors on the screen. In the era that Robinette was working on Adventure, I think everyone was okay with that. But you had to do a lot of really good timing to get more than those 4 colors out of there. There were actually 128 available on the palette, but again, this was the general expectation. It also, in 1978, 79, in that era, there's still a lot of kids who are looking on their old parents' black and white televisions. So high contrast was a lot more important than aesthetics and the use of color. So that's kind of another thing to think about here. It didn't take long before we all had color TVs with games attached to them, but there was that moment in history that had to be a consideration for the players. So here's the type of games that they were expecting. This is Combat. Good old Pong, which Atari, you've heard a lot about Pong this weekend and what Atari did with it. I like that years later, not too many years, but they rebranded this as Video Olympics. Way better than Pong, right? It's in color now. This is Robinette's first game. This is Slot Racers. This actually came out in 1978. I like pulling this up. These are actually 2 cars running through a maze trying to shoot each other, so it's a 2-player game. In game design, we like 2-player games. There's an issue with games and with player experience in games where as a player gets better at it, their skill gets better at playing the game, their skill increases. If the challenge of the game doesn't increase, they get bored. And probably anybody who's gamed has experienced that. There's this thing in contemporary gaming called grinding, where you just run around and try to collect stuff so that you can get more stuff so you can fight a boss later on. and it's kind of a boring part of gaming. When you have a two-player game, you have a live opponent, and they're not predictable. And ideally, say you're playing with your brother or sister, as you get better at the game, they're also getting better at the game. So the challenge continues, so it adds for more replayability. It's great, and it's kind of strange to me that for several decades, everyone sat quietly in their bedroom and played video games by themselves. Until, boom, here we are today, and everyone's doing this again, but we're doing it over the internet. I'm running all off track, but interesting pieces. Again, on Friday, I talked about this a lot, so I'm not going to spend a lot of detail on this. This is the way that the TIA chip translated the video signal from the Atari to NTSC standard video to tube televisions, right? There's a little gun in there that's flying back and forth that has to predict the timing of that, which is where you hear that phrase, chasing the beam, that's always associated with the Atari. There is no screen buffer. Every other game system I've ever programmed on has a screen buffer, which means that you can put a graphic on the screen, leave it there, go do some game logic in your code, come back and have some expectation that at least some of it is still there, or maybe it moved a little bit. In this, they're literally chasing the scan lines, and the processor is spending a large amount of time just getting the image on the screen, which means all the code in these games had to happen in the blanks, right? The blanks are when the beam inside the television turns off for a second and flies back to its next starting point to create the next scan line. So as it's flying right to left or bottom to top, you have a little time in there that you can add some logic to your game. There were 192 visible scan lines. When I look at Atari pieces, we still think in pixels, or at least I currently think in pixels. These pixels were not square, they're kind of short, flat rectangles. So you could get a little more information up and down than you could left and right. Left and right, it was timed with machine cycles. So you had 76 machine cycles. What that meant for the programmer was that the programmer had to know every time they put a command into assembly language, how many cycles it took to run that command. And that's fine, and we have charts and we can look that up. If I am loading some value into the accumulator, I know that that takes 2 cycles, right? Where the problem comes about is when you start branching or creating conditions in your code. If this happens, do this. Now I'm not sure what the outcome is, which means I don't know how much code I'm gonna run. I'm not gonna know where in the code the logic is jumping for the game. That's a bit of a problem. Atari did something really nice. They created this little piece called wait for sync, WSync. And what it did was, if you lost track of the code timing, you could put the processor to sleep, and it would wait until the next scan line and start back up again. So if you kind of lost track, or if you know that the logic changed the amount of cycles that it was going to take, you could catch up on the next scan line. It added a little bit of glitchiness, but that is a nice recovery mechanism, and I can't imagine how anybody would have done anything without it. Chasing the beam. I was thinking about it was probably easier to run across I-95 than it is to time these games. I should talk about this a little bit. So a lot of the diagrams and things that I have up on the screen here today, they're not officially released, right? But we all have them. There was a Stella Programmer's Guide written by Stephen Wright, 1979, we think. This is an internal document at Atari. It's awesome. I basically learned to code for this machine based on this document. It tells us all about the different registers, the timing, the different conventions that can be used. I wanted to bring it up because when Robinette was programming Adventure, he had already done a game, Slot Racers. Slot Racers was actually released a year before this was written. So I had to think about how the heck did these people figure out how this machine works. Obviously, they could talk to the engineers, right? The engineers are on hand. The engineers were not necessarily programmers. This is a different way of looking at the same problem. They did have some other documents. This was kind of an interesting one I found. This is the documentation almost a spec sheet for the TIA chip for the television interface adapter. Probably the most important piece of this. I find it fascinating that over half of this document is drawn and written by hand with a pencil, and then photocopied. So I can't imagine how often they realized things were changing in this document. I'm guessing that Robinette and some of the other programmers in this era probably contributed to this document instead of relied on it. I'm sorry, not this document, but the Stella Programmer Manual. Again, if anybody has any personal experience with that, I'd love to hear about it. Oh, let's look at this for a second. So this is Wil Crothers. So he is the person well known for designing Colossal Cave adventure. He was a caver. I find that interesting. Colossal Cave was based on a real cave. So Colossal Cave is in Kentucky. It's part of the Mammoth Cavern structure, underground networks and tunnels that apparently run all over the place. And there's a lot of really interesting articles out there that relate the game directly to this part of the cave, which is really cool. And I kind of like this. Anybody who remembers going to the down the hill following the stream from the well house and going to the metal grate, and I see many, many pictures of that metal grate that it actually existed, or still exists probably. You know, and that was all kind of based in reality. It's kind of fascinating. Obviously, Woods came back afterwards and added a lot of magic and mysticism and had never been to this cave. So there's that piece of it, too, that makes it so interesting. There's Don Woods. Translating a text game to graphics. This is the concept that he had in his head, right? When we play this game, and I have a couple different interfaces for it, because everything's happening through emulators in my life, whether it was on the PDP-10 or wherever it was ported. There are commands. There are lots of commands. I took a look at the early Fortran code, and yeah, there's some of them. There are over 150 typable verbs in the parser, and there are over 350 interactive objects in the code that you can engage with as a player. It's amazing. It's really cool. He had, compared to the Atari, a lot of room to work with here. So how does one play this game and then think to themselves, I'm going to move this to the Atari? So one of the things you have to think about is that interface between the player and the game. And we're back to this mess again, right? So on the Atari, pretty quick to figure out, there's 1, 2, 3, 4, 5, north, south, east, west. So those commands are good. In Colossal Cave, you just put the letters in, right? N, S, E. And then that fire button, which proved pretty useful. I think the most important command that everybody remembers is get lamp, right? So this idea that you could grab an object and then it has an inventory that's saving all of the elements that you encounter along the way. And you could have many at a time that you're carrying with some limitation. There really wasn't any room for that on the Atari. So he basically had to work with that button to make that happen. And it changed the way he viewed inventory. And he talks about this a lot in different talks and interviews. So you have your 5 commands here that the player can use. And then, there's a couple more that he figured out. This is pretty smart. So using collision detection, when 2 objects on the screen bump into each other, depending on if one was in control of the player, this could also be another command and an intention. And a really good example of that is unlocking the gate. In order for the gates on the castles to unlock, you had to move the key to collide with the gate itself. So that interaction becomes a new command. This is akin to saying unlock gate or use keys, something like that in Colossal Cave. And he did it in a couple other places. Pick up item, drop item, that's the one where you actually use the button. That's drop item, right? Pick up item is just slamming into it. Attack dragon or use sword is, again, it's based on collision detection. You literally just run into the dragon with the sword, and that's the command. That's the user interface. So he pairs 150 commands down to 7. And I think about that a lot, and I am a big fan of minimalism in game design. I think if the core mechanic of what you're doing is good, the rest of it's just fluff. That's the part that gets people immersed into games, that makes us really enjoy them. I know I spent a lot of time on Adventure trying to type, I'm sorry, not Adventure, Colossal Cave Adventure, trying to type swear words into the interface because I'm exploring the interface. I'm no longer exploring the game. But here, you're immersed in the game. It's a very different thing. There's an obvious object limitation that we have on the Atari, which is kind of interesting. This little chunk of code that I found lists some of the objects that you can hold. So you basically have 10 of them that the player can interact with directly. And then there's, again, a whole lot of other objects that you can have interaction with. These are the ones you can carry. So problem with the Atari is that the objects were limited based on those earlier games that I showed you. This was designed for Pong. This was designed for Tank. They originally thought that's what was going to happen with it. So you have 2 players. You have 2 bullets, right? So player 0, player 1, missile 0, missile 1, and you have a ball just in case you wanted to make Pong yet again. And this is it. So the Atari had 5 sprites. Robinette did some very interesting things, and when you watched me play in the beginning, the flashing that I talked about in the screen happened because of this. He realized that he could use some variables to split up the timing of when things showed up on the screen so that he could reuse these objects. And he managed to get, about 12 of them out of that. So you have your dragons and your keys and your magnet and your bridge and your player. And even more interesting, a lot of these objects had multiple states. They had multiple graphic states. So you have the dragon, and then you have a dead dragon that looks different, right? So he basically time-shared these registers and on the fly switched them, which I imagine turns into a mess when you start to have 5 or 6 objects on the same screen at the same time. You're suddenly running out of space. And I do remember things being very flickery. Sorry, I'm bouncing around a little bit here. Make sure I cover everything I was interested in. These are some more of the vocabulary in Colossal Cave. So again, we have about 350 different actions that you could use. There's the sprites. I got ahead of myself there. Right, so these are the sprites, but not the different states. This is kind of an impossible graphic, which is fun. Kind of hard to see the chalice here, but there's the chalice as well. Our Pong ball, right? The player was a ball. That leads to some other problems in game design, which I'll talk about in a little bit. There's some interesting things that happened in the world, and I'm sure anybody who's played this type of game probably sat down and tried to map it at some point. And anybody who's played Colossal Cave knows that there's some parts of that game that are impossible to map. And it's funny, for some reason when I was making slides, I was having a hard time getting to everywhere I wanted. Any room in Colossal Cave could have any number of exits as long as you had links, as long as you had a way to link to the next room. And they did not necessarily have to be right next to each other. You're not thinking about a real physical space unless you want to. That's pretty cool. And there's a lot of places in here. I can do north, south, east, west, so I'm running south here and seeing the different descriptions and then have a little interaction. And now I can go down, right? In Atari, we're talking about a 2D space. So there's a much different problem here. We have north, south, east, and west, and that's it. And that meant that there had to be a lot of cleverness in the map and how things relate to each other. This is a really interesting diagram. Chris Sanick, who's written a lot of interesting things about Atari. Are you here? That would be awesome. Okay. Made this map, and I really like it for a couple reasons. It kind of shows a spatial layout of the game, and there's interesting things that don't work right away. You know, the fake walls and the Easter egg behind the wall is kind of interesting. This doesn't show off very well that some of these mazes, you were actually playing in the dark. You don't see the maze while you walk through. I'll talk more about that in a little bit. Another thing that I found really fascinating about this particular one is Robinette had some interesting ideas about that moment when you get lost in the woods in Colossal Cave, or I'm assuming that he's associating to that moment. If you look at these letters, not the ones over here, but these alphabet letters, the paths never came out where you thought they would, right? So this is an impossible physical space that he mapped, which is really interesting for a player, right? Because we have a tendency to think about game spaces as real spaces. And so when you're suddenly jumping to impossible places as you're going through a maze, it becomes a much more difficult puzzle. I think that's a brilliant piece of work. This solves part of that problem of only having north, south, east, and west in your game navigation. Suddenly you kind of have this, I don't want to say teleporting, but you have this way to make the player jump around through space and have to deal with that as part of the puzzle. That's me getting lost in the woods, isn't it? This is another important aspect, and my students get to hear about this a lot. When we talk about game design, game players need to see visual information on the screen and understand very quickly what it means. As artists in game design, we think about two different approaches to this. One is that you could have a sign or a symbol, a way to represent an idea, something that we understand right away when we look at. Or you could have a depiction, meaning that the object on the screen looks a lot like the object in real life, right? And there are two ways to get information across to the player very quickly. This is a really easy one. I love this. Everyone looks at this and knows exactly what it means. It has nothing to do with the action of stopping, right? But we know when we see that shape and that color, we should stop. There's some interesting reasons for that. I think that this shape is an unusual shape in nature, so when we see it, it stands out. The color red maybe makes us think of fire, or something that's hot, or something that's burning, or the color of our own blood. So there is probably some physiological response to this, right? When you use certain colors, those colors become a symbol and have meaning. Red doesn't necessarily mean stop. It does to a 6-year-old. But it says, look at this. Pay attention to this. This is important, right? So the color becomes a symbol that has a lot of meaning. That's a very strong thing we can use in game design. Here's a different kind of sign. This has a different way of communicating to us. We recognize the shape of a truck because we've seen trucks in real life. It is sort of a symbol for a truck, but it works as a symbol because we can quickly identify it, right? And this kind of silhouetting that happens worked really well in early game design. So I think a lot of designers relied on this. We also know this truck's going down a hill, so we can imagine in our head, uh-oh, giant truck, big hill. So it makes us think about that. But again, that's happening because it's a depiction, because it represents the shape more than the idea. I don't pretend that Robinette knew any of this or thought about any of this. I think he was drawing things on the screen and then testing them, having other players play the game and say, yeah, I know what that is. No, I don't. This is great. He did a really good job with this one. I haven't met anybody who looks at that shape and doesn't understand that's a key, even though we don't use keys like that. I barely use keys at all anymore, but we understand what that is. okay, I'm not sure why there's a magnet in this game, right? When you first play it, once you lose something in a wall, you know exactly why it's there. But it works. I don't own a magnet like this. All the magnets in my life are on my fridge and have buttons on them, right? But we understand this shape to be a magnet, maybe blaming Wile E. Coyote. It works. We look at it, we can recognize it. It works a little better when we see the interaction. When we drop the key and the key floats across the room, we're like, oh, that's a magnet, not a horseshoe, not the chalice I thought I was looking for. This is a really interesting one. I mentioned it for a second and asked in the room. Never mind the key up here. Is that a sword or a spear? And everyone who I've had play this game without looking at the instruction booklet assumes it's a spear. It's an arrow. It's got a sharp end. You point it at a dragon. The dragon dies. That's the way it works, right? This was the intention of it. It's a sword with a hilt. I'm sorry, the colors are so dim up here. And a lot of people probably played this their whole life and didn't realize that's what was going on, that we have all been running around holding the sword by the blade and swinging the hilt at monsters. It's interesting. And, you know, I think he knew this. I think he knew this, and I'm sure somebody talked to him about it in testing. Spear, sword. Spear, sword. And I don't think it mattered. I think the job got done. I think you recognized it as a weapon, and that was the important part of it, right? I love this. So I have my students play this game. They're reading a little bit about early history in some of the many great books on the subject. And then I have this play this game, and I've tried, before they read it, I have them play it so that they have something to reflect upon while they're reading. And sometimes, every now and then during a semester, I'll have them play it afterwards, because they don't bother looking on the internet to see what these things look like. They're just reading the text. But I had this moment a couple years ago where a student of mine screams out, why is this duck chasing me? And again, Robinette was aware of that, and he's talked about it a couple times, you know, the dragon ducks. But it's kind of funny that happens, and we have to kind of think about what the symbol is and what he was trying to do there. It doesn't really look like a dragon. Then again, I haven't seen a lot of dragons, other than in pictures. It does look a little bit like a duck. It's duck-colored, so I can kind of understand where that happened. But again, the more important part is that there's something chasing you going like this with its mouth. You understand right away what that means in the game. And frankly, for somebody who's not an artist who was dealing with this problem, I think he did a pretty good job. So all of these graphics are drawn in zeros and ones. So they're literally drawn in bytes. You have 8 pixels across. Every time you have a 1, there's a pixel. Every time you have a 0, that's the background space or nothing, right? And so he managed to squeeze in these graphics. And if you kind of squint and lean back a little bit, you'll see that dragon in there, right? Here's his mouth. Here's his tail. And then all I'm doing is I related these X's to the actual ones and zeros in the code. Your sprites on the Atari had to be 1 byte wide. If you wanted something wider than that, you had to suck up more memory and use 2, or there were ways that you could quickly switch back and forth, which causes flickering, but at least you'd get a bigger picture out of it. Occasionally, some of the smarter coders in the closer to 82 and 83 would use the background and sneak in other objects there to get the same effect across. But this was a limitation. I think he did a pretty good job with the ducks attacking you aside. This is one of my favorite representation issues in this game. Something that I kind of love about Colossal Cave is that lamp. Because when you first go down in the hole, you're not thinking about it. You're thinking about other games. You just get a description. Here's a bunch of words coming at me. You're not immersed in it. But when you go down in that hole, it explains that you can't see anything when you pass through the gate. I don't remember when I captured this, but I probably died and reincarnated and came back, so who knows where my lamp was. But I like the idea that there's a dim light at the east end of the passage, and that I didn't really know it was there unless I had that lamp with me. This, and I don't know if people recognize this, so if you got into the level 2 and level 3 on Adventure, there are these mazes that you play blind. And the way they work is, so there's the player. The player always looks like the color of the background. It's almost like you have a flashlight or a lamp. You can see a small area around you. Oddly, you can see through maze walls, but I think that's fairly important to solving the puzzle. And you can see objects, even though there's no light here. So this character is moving in, is going to be forced to go down this passage and maybe come up here somewhere would be the goal. This is all done with bitmasking. There was never any intention in the design of the Atari to do things like this. And I think it's a brilliant piece of work. And I think it works really well. I think when kids played this when they're 7, 8, and 9, that's spooky. You can't see. You don't necessarily know if there's a dragon around the corner or not. It adds a lot to the game. I think it's a brilliant way of dealing with representation. There's a lot of different aesthetic things. I could go on a long time about this. I showed you the pictures of the castle without even mentioning it. It's kind of weird that you see the front of a castle on a top-down, but it also, again, it helps us understand that as a symbol in the game, and that's what's really important, is quickly communicating these thoughts. One of the other things that is really amazing about this game is the fact that he squished this whole thing down to 4K. And he did so. Probably half the people in here refer to this as crunching. You just need to get those extra couple bits or bytes out of it, and he did well. So this is the Fortran code behind Colossal Cave. I have a weird relationship with Fortran. I don't want to deal with it, but oddly, I can kind of read it, which is interesting. Fortran is it's not known as being a big language. It's fairly compact. I wish in some of my microcontrollers and things that I program that I could get away with a complex conditional statement in like 20 bytes. That's pretty cool. So it's a pretty concise language. The first version of Colossal Cave, the source code was about 32K. It's unclear to me how that ended up compiled for the PDB-10. I was able to look at a DOS port of the original game later on, and that compiled out to 94K. So that feels like a lot of space when we're talking about the Atari. So how did he do it? How did these designers compress all of this action into such a small amount of space? I caught a little bit of an interview with Robinette, and he apparently took a C class in college before he started messing with this. So he went from a higher level language down to assembly. And I think because of that, he looked at assembly very differently. So he has this really interesting scheme. This is a table in memory that holds all of these references to the rooms. Most of the rooms have about 15 to 30 bytes of information. And he's basically using this as a lookup table, which means he designed a pointer system. This is pretty brilliant. That means when you have something that's not moving around, you can store it in ROM, and when you have something that needs some flexibility to it, you can move it to RAM, and you can base it all off of this really well-organized table. I won't get into reading the code too much. I like this little piece a lot, too. So this parses the rooms. And something I realized from this bit of code, mind you, these comments were added later. So these are people later in history who are analyzing his code to try to figure out what the heck he was doing. And they did a pretty good job. A lot of people have worked on this particular piece of code. There is some really interesting math, and he figured out a way to basically create a formula where he could predict what room was going to be more north, south, east, or west of the room that you're currently in by just doing a little bit of math juggling. So the rooms had to be organized in a specific way to pull that off. I've seen schemes like this before. I honestly have no idea where he came up with it. It's brilliant, but I suspect there's a lot of other people in programming who do things like this. Nice little piece. That helps chunk down the sizes. Whoops, let me back up for a second there. I did not count bytes on this code, but Robinette says at the very end of it, he actually had out of the 128 bytes of RAM, he had 15 bytes left over. So he must have gone pretty crazy crunching that code and thinking about what he really needed. And a lot of people have kind of hypothesized that this could have been a much bigger game. But if you play level 3, when you start inserting randomness into it, kids could literally play this for days and days and days. You have, again, a 2-minute arcade game that kids can spend an hour doing one round of it and maybe not even win. I want to talk a little bit, I'm doing on time here, talking a little fast, I guess. I want to talk about the legacy, so where that all went, what happens after that, why I care about this so much. We know there's some direct legacies. So Atari got a licensing to do Superman when the Superman movie came out, which is around 1978. My dates are a little muddy on some of this. My understanding, and I jotted it down in my notes here, John Dunn was the programmer of this. This is one of the first games that we see where there are multiple rooms. If you're not familiar with this one, it's a pretty cool game. Superman can fly up and down into high sky-rise buildings, left and right across the streets, down into some subway tunnels, if I remember. You're chasing Lex Luthor, you're trying to stop a bridge from getting blown up, and you're avoiding kryptonite, and occasionally you have to smooch with Lois Lane to feel better. It's a fun game. The symbol work is pretty good. We definitely recognize that as Superman. You don't have to worry about that one too much. Licensing-wise, I think this worked really well. Dunn was given the prototype engine from Adventure to make this game. So he basically already had the table set up for the rooms and things and just inserted new content on this. So there's this direct impact on some other games that happen. I'm pretty positive that most of the programmers at Atari, and especially because of the political side of what happened, were keenly aware of this code and how it worked, and I'm sure they chatted about it and shared a lot of information. I think there's a good argument to say the people who left Atari and went to Activision, I'm sorry the slide's so small, this is Pitfall. Pitfall in itself, an amazing game, a huge part of history. But again, taking these ideas of multiple room adventures, working your way through giant mazes of multiple pages to get some treasure. There's definitely an impact here that happened. Again, no words. You know, you have a little bit of more information at the top. You know, lives, you know, amount of time that passed, and some score, which is probably borrowed back from the text games. I think there's a huge argument to talk about this whole franchise. I have not found out a lot about the programmers of Zelda, but when Zelda came out, there's definitely some influence from the Atari game on this. The style, this is definitely action-adventure. You have the same setup of this north, south, east, west that's happening. There's a little different approach to attacking, but on the NES, we've got sprites and sprites and sprites and sprites. You can do a lot graphically, even though it's on a very similar processor. The NES is on a 6502, but there's a screen buffer. You have a place to store graphics, and that changes things dramatically. And you can even get text on the screen. What would that have done to Adventure, right? This moves on to other platforms. I barely need to show these. It got moved to the Game Boy, I think, 1993. And something to think about with this is when we get into the 2000s and you start getting into 3D gaming on the PS1, those programmers grew up with an Atari joystick in their hand. Adventure is probably one of the reasons that they went in the career field that they went into. So by late 90s and 2000s, we see that happening. I suspect there's some influence on games like Doom, honestly, but there's no record of that. You know, I'm guesstimating the history of a lot of programmers. This is the latest iteration of Zelda. Breath of the Wild. You run around. You attack dragons and monsters. You go into castles. It's practically the same game in a 3D space. I think that's my last one. Yeah. I'm talking fast, so I'm happy to entertain some questions. Yeah.
Wait,
Oh, I'm sorry, go ahead.
Oh, yeah. So I guess like right around the same time, I believe a venture would be like Rogue on Unix PCs, and I feel like that is kind of the similar transition from text to
Yeah.
graphics based.
Yeah.
Anything to say about that?
No, absolutely. Yeah, so this idea of having graphic augmentation to the text stories, that's really important to me. And the same thing was happening on the Apple within a couple years. Yeah, that's really important, and I think that impacted a lot of players. It's a different type of player, right? This was mass marketed to families, so I think it impacted a wider audience. There's a lot, and I think there were some people this weekend talking about hyperfiction and how to tell stories in a space where you can make multiple decisions, and we're really good at doing that with words. This is a strong part of that change that I think. The symbolic representation that you see in the Rogue engines, yeah, very similar, and there's a lot going on, and I think that's really important. But I really don't want this to get lost from history. I think this is a big step. Yeah. Other questions? Later talks today, you're going to be hearing from people who actually did the work. I'm a historian talking about it after the fact, but I appreciate your time and glad I could share this all with you. Thank you.